Oh, hello there. Better late than never, I guess. Hey guys, what's going on? I apologize. I may or may not have gotten caught up on Professor Brian Keaton in interviewing Avi Loeb, who's fresh off his Joe Rogan experience, and we all know it's totally aliens. Um, I enjoy listening to some of the things, and I'm not gonna lie, I mostly listen just because I know there's gonna be drama and stuff like that. So within the first 5 minutes, it's like, well, another Brian, Mr. Brian Cox, and I'm totally not just saying those names just because it's the first minute or so of the video, and you gotta name drop all those things. I totally am. It's welcome everyone. I apologize. We'll get into it. So I saw you, David. There, David was commenting earlier that I'm not sure I have any fine structure constant jokes. Well, I believe in you. I'll leave it at that. The suspense is killing. Okay, again, full disclosure. This is speculation. Like Professor Loeb, I'm pretty sure his betting odds are it's most likely a comet. But if it isn't, and your level of credence to the percent chance of it being comet, being maybe a weird comet, to being aliens, may vary. Okay, so now that we're at the 137th second, let's actually get to the whole dang point. Uh, Rick is saying, that's an error. Welcome, sir. All right, let's just get into it. And again, most of this is just because I'm procrastinating. I need to finish cleaning up my Wolfram Summer School project because I'd gone through it and fixed like most of the generic errors and touched up a little bit, and then it's like I'm supposed to be presenting on Friday at the Institute, so I need to make it look pretty. I need to make it look pretty, and Dugan, when he had messaged me, I apologize if I'm sharing, but every time there's some people you talk to, and it could just be a very short conversation, and you're like, oh my god, I got an idea. That says that happens occasionally with me. Like I'll just be saying random things like, oh my god, I have an idea. It's like I have that effect. Dugan has that effect on me. It's just like it just gets me to think, and then I'm like, oh, duh. But I digress. All right, so what are we talking about? Okay, I said this claim. All right, what is our claim? The claim is that all right. Let's just do the blatantly obvious thing. Let's just show our little banner because it's basically got all the information right there. Okay, it's again, it's not the flashiest thumbnail. A lot of stuff. It's like why the heck would I click on this? Unless literally I look at this, I can see well enough and I can read that little text. Okay. For those of you like me that what the heck am I doing? Oh god, no. Not that thing. Alright, undo. Sorry, I'm playing with the actual image. Okay. Yes, I swear I can occasionally talk and do something else. Okay. So the claim is, and I'm not going to say this is the limit of the fine structure constant because ultimately, if you're going to go to, I don't know, like past grand unified, or maybe this is attempting grand unified. Actually, no, I'm not going to say that because this is the quantum electrodynamics limit. If you want to go quantum, long story short is ultimately at quote unquote unity, you would expect things to be one. Okay. So that's why I said the QED, the quantum electrodynamics limit of the fine structure constant. Question mark. Okay. To be fair, I probably never would have looked at this because I originally had heard it's like about 1 over 129. Rick at one point had commented it's about 1 over 128. Okay. To be fair, if Rick Hannons has said that, I may not have even looked at this. So again, I have no idea if there's any there. I'm just doing the very basic thing and seeing if something interesting happens because again, I'm sure somebody's probably seen this or something, but do we really discourage people from trying to do things? I don't know. Okay, so the whole claim is here. All right, there's a QED limit. Ultimately, I got this answer, and then all of a sudden I'm like, that's kind of close. Let me see. So I tried to look it up, and basically what I got from Wikipedia was right here. Basically, let me embiggen this. Okay, so basically, and again, that's from Wikipedia, take it for what it's worth. Okay, so basically the normal alpha is basically at zero energy, or the coupling with the electron, because that's literally its definition. Elementary charge divided by the Planck charge squared, you get whatever your probability is, and just that standard ratio is the amplitude. Okay. I'm repeating a bunch of words that have been drilled into me. Do I know what everything means to the full mathematical extent? No. But I can at least start to put these things together and try to start parsing what might be going on. Or if I can at least replicate the calculations and stuff, it's like maybe that's a good first step, because Professor Feynman had said, calculate everything that's already been calculated. I don't think I have time to do all that, unfortunately, but I think the general ethos of what he was saying is go through and at least attempt, like, work through the calculations, see what other people have done. Okay, then go from there. All right. So basically the claim is, at higher energy, such as the scale of the Z boson, about 90 GeV, one instead measures the effect of alpha to be about 1 over 127. And to be fair, that's probably a cop-out, because I'm taking the Higgs boson, because basically that's basically the magnitude, or at least if I'm going to follow the own BS that comes out of my own mouth, and I'm like, well, if elementary charge divided by the Planck charge gives you J1, aka the amplitude of the fine structure constant, you square it, you're about 1 over 137-ish. I'm like, all right, if I take the Higgs mass divided by the Planck mass, all right, I don't know what that means, but if I were to assume there was something there, I'm like, all right, that seems like the amplitude of something. What is it the amplitude of? Square it. Get whatever your probability or however you want to frame it as. I'm like, seems to be the magnitude of h bar. Planck's reduced constant, the elementary unit of action. I'm like, could the elementary unit of action, and step back. All right. The whole claim is normally you take elementary charge, you divide it by the Planck charge. So you got an elementary thing divided by a Planck thing, squared, you get an important number. All right, that's like the Higgs mass. And I divide it into the Planck mass, square that whole dang thing. I'm like, all right, it goes up to, what? It seems to be the magnitude in at least first several significant digits of the elementary unit of action, without dimensions. I don't know. Is that the amplitude of action? I mean, how does all this stuff work? And again, I understand. You got your sombrero, your Mexican hat potential. There's some spin. The other interesting thing is when you're calculating the Higgs bosons. Basically, when I'm going by setting these individual particle thingies equivalent to h bar, the difference between the Higgs Compton wavelength and that setup is actually a factor of like 2 pi. So I'm like, why does the spin zero thing have a circle in there? Again, hopefully I'll get a chance to speak with smarter mathematical minds than myself at the conference, and be able to maybe see if there is some, hopefully simple, group structure and or rotation-based thing that we can fit into the standard model and be like, okay, maybe we can computationally reduce this. Maybe if we can take out a whole bunch of loops and everything that take a lot of I'm just looking for simplicity. Okay. I've been rambling. Okay, so long story short is fine structure constant is that thing about 1 over 137. All right, the QED limit, the claim is, or at least what I'm claiming here, is it's about 1 over 127. Why? Because this is the result that we get when we do this crazy dang thing. What did I do? It's like, I tried playing around with these. Okay, let's stop just being lazy and sharing a screenshot. So, oh, okay, no, that's fine. No, I'm just saying, Rick, that you were closer to this number. If it wasn't within that, I may not have checked. So I'm like, that's too far off. It's so. Hey, welcome, K-Shaw. No, we're just we're conjecturing. It's hold on. We need to play a thing because we're conjecturing ahead. Oh God, so many things. Here we go.
Although this is going to be weird, and it's going to be about a different.
Title of the conference was something like "Ground Truth" or "Turtles All the Way Down." And so it seems as though there's one rule I don't think it rules them all. And it might be
instead
just
instead
hyperruleal turtles all the way down.
yes, it's on the back of an infinite number of hyperruleal turtles.
Various people are commenting on the outrage of hacking the universe on a MacBook Air.
There we go. We've covered our bases, so to speak. All right. Let's see. Where are we? Mark is commenting. Void, mass, space, and time. Infinity in all directions. Are we all at the center of the universe? We don't assume that. However, if we put our reference frame in there, if we assume the Earth was the center of the universe, maybe we could explain a bunch of that. I don't know. I'm not assuming that. I'm not assuming we're special. I don't know. I think this... You run the things, it's like, all right, you have to have a realm that is within a particular range, because if you were to vary the constants within the fine structure constant by, I don't know, like 5 or 10%, it's like, yeah, a lot of things would start getting weird. You're not going to be able to have the elements as we know it. Oh, okay, all that stuff. We have our realm where life, as we know it, might be possible. All right, let's go through that. You have that. You need to have some form of a system, maybe a solar system. Maybe you could do it with a binary system, but if you have the singular, standard M-type star, is that what we are? I think we're an M-type star? I forget. You have a star like our sun, and a fairly non-chaotic thing with a whole bunch of supernovas always going off around you and everything. You're going to have planets. You're going to have them within the quote-unquote habitable zone. Again, as we know it, who knows what life may or may not be out there. And then you start to get a system where you may have liquid water. And if you have liquid water, which coincidentally at a particular temperature and density is precisely 1 cubic meter equal to 1,000 kilograms, just putting that out there, totally self-fulfilling reasons. But, okay, you do that, and then you're going to need to have some form of, I don't know, maybe protection from ultraviolet light, or have a deep enough ocean with a particular chemical composition and everything that wouldn't be toxic to, again, life as we know it. Okay, and then maybe you're going to need something to block from too many life-ending the collisions and stuff. So you're going to have a big brother, maybe like Jupiter or something, it's going to be a bit of a gravitational sink, if you would. It's going to be your blocker from a bunch of meanies or folks throwing stuff at you, potentially. I say folks, I'm being hyperbolic there. Who knows? Professor Loeb may disagree. I digress. But then, maybe if you also happen to have a moon that, I don't know, for some reason, how do you get a particularly large moon? Well, you have to have maybe a sister planetoid or something potentially crash into you, ejecting, mixing up all these different things, and then you have a very massive moon that can also act as a buffer. Apparently had some electromagnetic connection when it was still, like, had its electromagnetic properties, according to some surveys of some moon rocks. I don't know. I didn't do the analysis. I'm not an expert in those things. I do not have a PhD in physics nor mathematics. I'm a crazy person on the internet that's interested in these things. Perhaps, like you all are. And then you're going to need to have the generation of a particular process that is still unknown to us, that you literally would have simple organisms, blah, 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 continuing to adapt, evolve, and just go through generation and generation, and eventually you have adaptation into... I don't know, flesh bags like us, a whole bunch of apes that can mash on a magical keyboard and attempt to do something cool. Is there actually something cool there? I don't know. The statistical chances, to sum up, it seems like being here, just us, is a miracle. I think the statistical likelihood says that. I don't know. That's a conjecture there. Aloha, Elena. Elena, yes. Perfect cow sphere. Yes, the Higgs cow. That was on the spherical god cow. That's I'm going to give a talk on that in a monastery just because it's such a ridiculous thing and it matches data pretty well. Hacking the universe should be done on a Linux. I'm not going to disagree. I'm not going to disagree with that, but okay. Let's get back into the whole dang thing. All right, so where were we? All right, let's share with the class. All right, not that one, this button. All right, so this guy here. All right, don't mind me about Landau polls and everything. All right, so this was our where was it? Potential variation over time. All right, so that was changing constants. Present rate of change. All right, that coincidentally about 10 to the minus 17. Oh, that might be interesting. Okay, maybe that is going to some of the Wolfram iterations. All right. Yeah, editing conjecture was about 1 over 137. We have looks like Thad's Joe 1 there, or the way that Professor Feynman liked to think about it. All right, he actually includes the uncertainty, which is good. At least that's according to Professor Keating. That's a big thing. All right, we go into all the legend. What's that? There we go. All right. So variation with energy scale. Let's just go over this real quick. Again, this is Wikipedia. Take it for what it's worth. Maybe this is all bunk, but this kind of seems to be similar to what I've generally heard. In quantum electrodynamics, the more thorough quantum field theory underlying the electromagnetic coupling, the renormalization group dictates how the strength of the electromagnetic interaction grows logarithmically as the relevant energy scale increases. Sounds like logs are useful. The value of the fine structure constant alpha is linked to the observed value of this coupling associated with the energy scale of the electron mass. Well, okay, imagine that. It's using its elementary charge, or the protons, but the electron's mass gives a lower bound for this energy scale because it, and the positron, is the lightest charged object whose quantum loops can contribute to the running. Therefore, 1 over 137.03600, yeah, because it's 999, yeah, is the asymptotic value of the fine structure constant at 0 energy. Okay. At higher energies, such as the scale of the Z boson, about 90 GeV, one instead measures an effective alpha of about 1 over 127. Okay. Again, they're saying higher energy scales, such as the scale of the Z boson. I mean, I'm just using the Higgs thing because that's what I was playing around with, because I'm like, well, if this seems to be related to the electromagnetic coupling constant, might we, again, grandest idea, most charitable interpretation, can we find a coupling between mass and action? Aside from it just being in the definition of h bar. It's the Planck mass times the Planck length squared, so it's a mass area divided by the Planck time rate, aka it's energy times seconds, because it's action, and then that action can help lead to some form of energy. It's kind of like, what is it, F equals ma, except instead of the acceleration, it's momentum over an area. So that would mean, why momentum goes through, okay, I was kind of thinking about this, why momentum goes through space-like hypersurfaces, and energy goes through time-like hypersurfaces. Okay, that is the extra part I need to add to my paper, but or my forum post or whatever. Okay. So let's go back over here. Let's get into the whole jazz. What are we talking about? Okay, so after playing around, hold on, let me make another thing with this. We'll get into the more precise things that may potentially be telling us more. So long story short is, okay, let's just start with these guys. So what we do is, you can get a ratio. These are 2 Planck units. And again, we are combining these ratios. You get the electrochemical equivalent. I saw somebody that actually did this, and they were proposing some coupling. I don't know. I don't know. It was interesting. I took some of the, I think I have it saved somewhere. But this is a ratio between different things. So for instance, again, within our coherent unit system, you have something like Planck length divided by the Planck time. It gives you the speed of light. It's the minimum of length per minimum unit of time. Gives you a maximum of speed. Cool. So we've got the limit of mass. Again, it's the maximum. If you cram it into a Planck volume, you're going to technically just try to create a black hole or whatever that object that seems to appear from general relativity is. Okay. Or lack thereof. Okay, so we've got the maximum mass divided by the maximum of charge. So the limit of mass divided by the limit of charge gives you this number. Okay, electrochemical equivalent. Okay, there we go. All right, so let's look at the other things. We can do the same thing. Higgs mass divided by elementary charge. All right. Gives you this number. All right, this is an even bigger number because, well, both these things are... Well, this is a... Yeah, both these things are smaller than each of them. All right. We look at these things. So I play around a bit. I try to see if I can find some interesting relationship. All right, let's do this. Just playing around. I'm like, all right, I don't know about that. I'm just literally hacking away in the dark. That's why some mathematical problem. I'm like, well, let me take the square root of this. Oh, that doesn't work out. The dimensions don't work. Oh, wait, I needed extra brackets, don't I? There we go. That's why. All right, that should work. Okay, hold on. I'm curious what the inverse of that is. Okay, never mind. I'm like, all right, let's do that. So I'm thinking, all right, I got 4 things in here. Maybe something would show up at like the 4th root, but nothing I can make sense of. And I don't know. Do I need to square this whole thing again? I mean, that's just seems to this root. Take the square root of the whole thing again. I mean, it just seems, yeah, it seems to be just getting ridiculous. So I didn't know what to do. Then I'm like, all right. Sometimes you'll see matrices and stuff, and it's like, all right, we got this thing here. You'll have like some diagonal or something. I think that was my inspiration, at least. Aside from just arbitrarily just playing around and looking to see if maybe there was something interesting. All right. How do we get here again? All right. Oops. Okay, let's go here. I apologize for jumping around so much. So long story short, I'm like, well, what if I took the Planck things? Let's just take the Planck limit of mass divided by the Planck limit of charge. Okay. And let's take the ratio between the claim is an element, or at least the one elementary gauge boson that exists everywhere. Basically, our only elementary scalar boson that we know of. Okay. And divide it by the elementary unit of charge. All right. So long story short is you're multiplying the Higgs mass times the Planck mass and the charge of an electron or proton with the Planck charge. Okay. And then you're taking the ratio between mass and charge. Okay. You get this ginormous number, like 16,000 kilograms. I don't know what this means. It has no interpretation. Okay. So we take the square root. Oh, skip ahead. Sorry. We take the square root of that. Okay. It gives me this thing. I don't know what that is. I don't get anything. All right. So let's do the naive thing. Let's divide the dimensions out. It's mass divided by charge. Okay. Let's just do the naive thing. We'll divide the whole thing by kilograms divided by coulombs. Okay. And then basically the rounding kind of lines up and, 127. So I'm like, that's interesting. So I mean, I just divide the dimensions out that way. I mean, it stopped me from doing the inverse and putting the ones, or the reference ones of the system, in the numerator, making it 1 over 127. Or this thingy right here. Okay. I mean, this really isn't that satisfying if you think about it. All right. So that's why we do it a little bit more deeply. So, not that guy. So if we actually take, we take the numbers from CODATA. Well, from these are now defined, or at least elementary charge is defined, and then the ratio between that and the Planck charge is the fine structure constant when you square that ratio. So basically these have 10 significant digits. I threw in basically the digits from CODATA for the Planck mass. So again, it's basically should be a deviation of about 2 in the last digit there. And then the claimed value of the Higgs boson, if we assume the ratio between the Higgs mass and the Planck mass, because at least on Professor Carroll's recent solo podcast on, was it fine-tuning, God, and a bunch of problems, he's like, well, if you're going to relate something, you would have something elementary. It's like, let's say the electron has a particular mass, I don't know, 9.1 times 10 to the minus 31 kilograms or something crazy like that. It's like, what does that mean? If you had a Planck unit, then you could divide it by the Planck mass to get that ratio. I'm like, okay, if I do that, I square it, it seems to, oh God, I'm just rambling here. Let's show this. It's like, all right, so if you take Higgs mass by the Planck mass, gives you the difference there. There's our 17 missing orders of reality according to PBS spacetime. We square that thing. Okay, we get a minimal amount of information. But that minimal amount of information at least appears for 3 significant digits again. It's only so much here in this, but seems to be all 1 of the reference dimension. What if we take the most recent measured value, or at least value of the Higgs that came up by CMS earlier this year? 125.38 GeV divided by speed of light squared. I get a mass. What's that ratio? What did I do wrong? Oh. I did, I put it in the wrong place. It's supposed to go here. Because that was the thing I calculated. There we go. So we'll do the same thing. A computation. All right, we get an extra significant digit. Okay. It took away the estimates, but again, you can't, there's not enough data there. Basically, it fits a lot better. Because if you look at the 4th significant digit, the first 3 significant digits are of h bar 1.05 times 10 to the minus 34. The next digit is a 4, but then it's, I think, followed by a 7. Because if you grab more digits here. Okay, it's followed by a 5. So technically, if you got 5 or a little bit over there, technically, it could round up. And again, that's only limited information. And that's a claim, and we would have to, again, have more experimental. Basically, we need at least a couple more significant digits. Verification, different experiments and everything before you can really fully assert the claim. I'll claim it just because it might explain a lot, and again, it's basically my MacGuffin, let's say. Okay. So that's just that relationship there. So let's go in and actually put in the numbers. So the same thing we did, we'll go step by step. So claim is, this is the calculated mass. Based upon that claim, of the Higgs mass. So we've got the claimed Higgs mass here. We've got the Planck mass from CODATA. We've got the elementary unit of charge, the Planck charge. Let's put these ratios together. Okay, we get a few more significant digits rather than just 1600. Okay, we get some extra data. But it's still in a dimension I have no idea what the heck that is. So we take the square root of that. Let's get it down. Now, we were multiplying what it was called an electrochemical equivalent. Why? Because we're relating mass to charge. Okay. That's how we parameterize it. It's the electrochemical equivalent. Maybe it's important for something. I didn't put enough brackets around the whole thing because I'm bad. See, this is why sometimes I go insane with the brackets, because it's better to have them and not need them than need them and not have them. Typically. All right, so I get this number here. I'm like, I have no idea what this is. And I'm like, 127. I'm like, well, this thing is relationship. This over this squared is 1 over 137. I remember someone saying, and basically me hearing something about, yeah, it's limit. It goes to like 129-ish. Yeah, it's not really that close. And I think Rick had mentioned something about 128-ish. And I'm like, I mean, that's within about 1 of 128. And I'm like, all right, well, let me just see what they at least say, at least on Wikipedia and some other places and stuff. And I think it's basically just taking that from maybe a respected person's blog or something. I forget if I had fully tracked it down. I'm like, okay, I got this number. I'm like, I'm like, all right, so it could be about 127-ish. I'm like, okay, well, this is 127-ish, and it's the electrochemical equivalent. And then it's still got dimensions. So why don't I just do the naive thing? It's just divide it by I should just do it here rather than just jumping all around my prepared tabs. Just divide it just like we did before. Kilograms divided by coulombs. Because those are the reference ones of our system. Okay, now it gives a dimensionless number. 127.232, whatever that means. Okay. I don't know what that means, but we got our 127-ish. What would it be if it was that? If we had literally treated it like 1 over that. So we put our reference 1s in there. We get this number here. That's about 1 over 127. Does this match the coupling constant of quantum electrodynamics to its limit? I don't know. Let's see. QED, line structure constant. Let's find its limit. To be fair, there's probably a calculation here that I just totally missed. I just thought this was kind of a cool thing. Again, to put this in a YouTube video to put it into a full paper, I'm gonna have to actually go through and do all the calculations and everything like that. So, current advances, blah blah blah. New determination. Okay. I want to see. Oh, it does not have a limit, at least according to this, in the traditional sense, because the value. Okay, QED limit. I know, yeah, they give these charts, but this is off. Oh, that's a slightly different one. They had a chart from one of those old school physicist, I think, bloggers thing. So, I honestly, let's try. Okay, yeah, so that's how we can get up to a maximum theoretical elements of 100, element 137 or whatever. Or at least it is claimed there. Okay, I'm not. What the had the 127 thingy there. Okay. This was from this guy. Okay. Fundamental constants at high energy. Okay, so this is a one author pay. Okay, well, it's the guy from CERN. Okay, so as of this, which was from, okay, about 127.5-ish. This is the error. Okay, so that's just the mass of the Z boson. So, okay, so I should probably not be lazy and actually go through and. Okay, so this is a while ago because they had a value of. Okay, yeah, this was this was before the actual discovery, or at least believed to be the discovery of what. Yeah, this was a decade before. Okay, so this might be. Oh yeah, and that alpha is. Okay. Yeah. Wow, this is an old thing. I wonder. Okay, so we should be able to actually calculate this out. In terms of the number of fundamental constants, standard model, blah, blah, blah. Number of flavor. Okay, that's looks like a Q. That's going into QCD. Okay, that's pure QED. The presence of only the photon field and the electron. The relative value of alpha is given in momentum space. Okay. By alpha. All right. The effect of alpha for charge squared equals alpha 1 minus alpha divided by 3 pi natural log of negative charge squared over A mass of the electron. And A is the exponentiation of 5 over 3 minus charge, comma, charge squared is greater. Oh, are we modding that? 5 over 3 and negative charge. Okay, so negative charge squared needs to be over there. Okay, so we can just do this. All right, let's just do this. Wait, no, this is only the electron. It's a renormalization group. Oh, wait, no, we should be able to calculate that for charge. I did that the other day. Why am I being lazy? All right. I don't know. I tend to screw up very often when I'm doing a new calculation live, especially if I'm not familiar with it. All right, so let's just do this. Well, from alpha. What do we need? All right, so I'm going to pull this out for just a second, just so I can actually see it. So, all right, so we got our effective alpha is charge squared. Okay, so let's do, we want charge squared, so that's energy divided by voltage. So let's just do that. So let's do energy, 125.376 GeV again. All right. There's a difference of 2, or uncertainty of 2 in the last 2 digits. All right, so let's divide that into the Planck voltage. Planck voltage. So it's going to be enough significant digits. Let's just go with it. All right, so let's do this. All right, so we get Planck voltage. All right, so now we've got charge. So we've got this. This is the charge. All right, so we want charge squared. Square that thing. Okay, it gives us this. So the effective alpha for charge squared is equal to. All right, so fine structure constant divided by 1 minus alpha. I'm wondering where this 3 pi is going through. That seems like a I don't know. That's 360, 460, like 540 degrees rotation. All right, so 1 minus alpha divided by 3 pi. Okay. And then we have the natural log of negative charge squared. Okay. So we're going to do natural log of negative. We need negative charge squared divided by that alpha thingy, which is, God, so many, or that A thing. That effective is the exponential of 5 divided by 3. Okay. exp. It's 5 divided by 3. Okay. The mass of the electron squared. Almost there. Okay, so the exponentiation, still got this in brackets. And then electron mass squared. Okay. So we got that. That's there. It's the natural log. And okay. Let me just check all the brackets and everything. Where are we? Okay. So we just hit enter. It's probably gonna be easier that way. I probably screwed up. Okay. I mean, this isn't gonna make any sense here because, well, I set something equal to something, and I didn't have an x. All right. Okay, so let's go back here. Make sure we're doing this right. All right. So I've got that charge. So we got alpha. We got our fine structure constant. Oh. Or am I just supposed to solve for alpha? I'm stupid, aren't I? Okay, so we got... All right. So, sorry. Alpha over 1 minus alpha divided by 3 pi. 1 over alpha divided by 3 pi, and then we're taking the natural log. All right, natural log of charge squared. So we got that. Oh, wait, that's supposed to be squared, isn't it? Oh, I didn't do that there. All right, it's supposed to be negative charge squared. Okay. Let me see. I think if I put that there. Is it negative? Where's the negative go for charge? Okay, so it is negative charge squared. All right, squared. And then negative charge squared. That 5 over 3 thingy. Okay, this natural log is supposed to be all one thing. That's why. And that shouldn't... Why is it putting all that below? Oh, charge squared, and then it's just... Okay. EXP 5 over 3, and then just that. EXP mass of the electron squared. Okay. Let's see if something comes out there. Okay, I don't know what this is, so I'm assuming that's going to be the effect of alpha. Ah, so we're supposed to be solving for it. Okay. Can I move this minus sign outside? Is that going to affect the whole expression? Okay, I think it affects it too much. All right, so we want the effect of alpha. So, oops. so let's solve for x. X for our alpha, and then our other alpha should be here. All right, so we're going to solve for the x. That fills that in. I might need to divide the dimensions out. Because does this come out to be a dimensionless thing? All right, so... Okay, we've got charge. I mean, we've got charge over mass here. We got charge squared over mass here. Okay, that just beckers the question. What happens if we just do that? Oh, we're just going to get the charge over mass ratio. What is the charge over mass ratio? 3 charge over electron mass. I did this before. Oh yeah, that's the... I'll give the electron gyromagnetic ratio. That's charge over mass. The mass over charge, okay, that was that 10 to the minus 6 number, I think. Okay, never mind. That gives us that electrochemical equivalent. Wait a second. Why is it so close? Higgs mass. I think. Oh, no. I shouldn't. I meant Planck mass. Although that is interesting. Okay. I'm sorry. I'm just playing again because I know there's something I missed. Just because there's something very noobish. And this ratio is just... Okay, that's the gyromagnetic ratio. Let's go back. Elementary charge over electron mass. Okay, so this will give us a 10 to the 8 ratio if I do Higgs mass divided by the Planck mass, because it's 10 to the minus 17, so this should give us a factor of 8. Okay, close to 0.6. Okay, I mean this is just... I didn't see anything here, I'm sorry. I'm just going through. Okay, so I probably need to divide these dimensions out. Unless if I do this. Okay, but we have dimensions here. Okay, that's chart. Oh, wait a second. I missed something, didn't I? Charge squared. Why is it the mass of the electron? We need to cancel out mass. This doesn't make sense. Unless I expressed it as energy divided by energy. Oh, wait, no. Charge has a mass component. Dictated by the ion pairs can be quarks, antiquarks, smaller distance. Alpha's becoming larger. This effect can be also seen. Increases energy, eventually repeats to the point where perturbation barrier breaks down. Okay, so this is basically exactly what they have on Wikipedia. Variable 3 charge line. Okay, there's increase in coupling constant happens at a much higher rate. Already at energies reached by the large electron proton. Was the electron proton accelerator of the order 200 GeV associated with value constant more than 10% higher. Okay, so that's about 100 and... okay, the present limit of the Higgs is... Okay. The standard 18 basic constants of the standard model: mass of the electron, mass of the muon, mass of the up, down, muon, charm, strange, top, tau, bottom. Up, down. Mass of the W. I think that's the mass of the Higgs. It's usually now small m, big H, 0. Alpha, QED, alpha. Burp. Strong, alpha weak. Intrinsically related. Okay, the nature of most of the fundamental constants seem to be intrinsically related to the generation of matter. Okay, hold on, let me share this paper. It's for anybody interested. This is basically what some of the Wikipedia articles. It's literally based on an article. A single author from CERN, but I mean, this apparently seems to be the best analysis that folks were able to find, or at least maybe folks haven't gone back to visit it. I'm just saying this is literally 10 years before the Higgs was discovered. Giving the coupling of those fields to the scalar boson. Okay, blah, blah, blah. Number of flavors, blah, blah, blah. I don't want to do the quantum dynamic coupling constant. I'm having enough trouble with this guy. Let me see. Does anyone have any? All right, we'll see you, David. Universe is open source or open sauce? No worries. Hey, take care of yourselves, Charlie. No worries. May the force be with you. Kalatu Barada Niktu. Yes. All right, I apologize. This is going into more of me trying to deep dive and actually see what might... Okay, in pure QED, the essence of the photon field. Okay, we got a charge squared. Okay, charge squared it would have a mass. Let's do this. Let's break this apart. First off, let's make sure we're actually getting a charge. All right, so time times current. That is charge squared. Okay. Charge has no mass. How the heck do I get the mass out of that? Or that doesn't seem to make sense to me. What happens if it's negative charge? That's for some reason. Okay. I was gonna say we're pulling a dimension out from the literal ether there. We want to solve. Is that supposed to be the mass of the electron? Okay. I mean, that's not going to affect that, just because that's dimensionless. Electron mass is squared. Oh, in momentum space. Okay. So, I think that sounds like they're talking about, I think, the Schrödinger equation. Let's see. First off, let's go back. Before we attempted to solve for x, that's a whole bunch of random dimensions. I'm going to try something very weird. Don't mind me. It's divided by the Planck momentum. All right. Let's see what the actual dimensions are. Giga electron volts. Oh god, it's not even listing them. This is not a good sign. Oh, it's moving the chart. Okay. So the dimensions are GeV. Okay, so we've got GeV squared. Oh, okay, let's over here. Mind me. GeV squared. GeV squared. Let's see where my mistake is. I know, it got really boring. I'm I'm attempting to do the Feynman thing. Try to calculate the actual things. If I said those words earlier, maybe I should have listened to my own words. All right, so that's divided by electron mass squared, Planck voltage squared, and then c raised to the 4th. All right. Let's see what the heck dimension this gives us. And I think this is technically an inverse. Okay. We get a thing. Inverse electrical voltage squared. That seems like something we can work with. Take the square root of that. That looks kind of interesting. Current responsivity. That seems like maybe what we're looking for. 1 over reciprocal volts. What? But 1 over reciprocal volts should be volts, right? Or is this volts? Flexoelastic ratio? Radiometric detector spectral radiant power sensitivity. Well, that sounds like a measuring device. Current responsivity. Well, let's put in our answer. It gave us an answer. But we're taking the logs of those things. That I had my log in the wrong place, don't I? No, it wants to take the natural log of that. This is again momentum space. This is also the first couple of digits of the Planck charge. Hold on, let me just... .875, 0.87. Okay, it's different enough. That is like the 4th and 5th digit of the Planck mass right there. I'm sorry. I'm just numerology. Okay. So we've got those things. I got a dimensionful thing. Bye-bye Planck momentum. Okay, that didn't work. Divide it into the momentum because the inverse of momentum is the two-dimensional Schrodinger or two-dimensional bound wave equation or whatever. So multiply the dang thing. Okay. So honestly, I don't know how to... What if I just saved all the dimensions for the end? It's taking the logarithmic form. Charge squared. Wait a second. It's energy squared divided by charge squared. GeV squared divided by coulombs squared. Gives you electric voltage squared. Okay, so that shouldn't be... It shouldn't be... How the heck? Or... Wonder, did they just do the calculation? Because Wolfram Alpha didn't exist at this point. You can just do the calculation and just stick the dimensions on at the end, but you do a log of dimensions. It doesn't really work unless you're raising them by the... Okay, I'm just going to do the naive thing and just strip all the dimensions out. I mean, this is... Oh... All right, let's just compute all that out. So let's just do that. do all this, and then we'll just take the log and we'll stick the dimensions back in because, well, that's the only way I can figure to do it right now. Now, this makes me wonder if we're not doing ourselves a disservice here, or if this even makes sense. Okay. So, got that. Those are our values. This is so dirty. I'm gonna do the log of this. The exp, the exponentiation. I'm wondering if that's even. Hold on. I'm wondering if I just exponentiation. It shouldn't. Oh no, I did the right thing because that's the natural log. That's the exponentiation. Okay. Okay. Gonna take the log of this thing. All right, let's do this. Let's do our dirty little. We got our number here. Let's throw it back in. Oh, this is so wrong. Okay. So that's what we got when we throw our stuff in there. Now we need to let's throw that. Let's just throw that just dang number in there. It'll be dimensionless if we just throw the original. Hold on. I know, see? See, look at how discombobulated I am. Benefits of quote-unquote live science. Alright, so we got that number. Do the absolutely naive thing of throw this just whole number in here. Okay. That's the number we get. We can take the natural log of that. Got our alphas. Let's see what the heck this does. Alright, so I have no idea what this is. So we're finally doing what was it? Okay, so 1 minus alpha, 1 minus 1 minus alpha. Hold on. It should be this. Don't tell me that was my total error the whole time. Okay. That actually makes... That got weaker. It's not right. It should be 0072. Should be getting larger. 1 over... Yeah, so it got weaker. That doesn't make any sense. Sorry, I'm sorry, I'm crazy about closed forms. I look spends far too much time for these things. Oh, look. 20 tetrahedral angles. Just collecting things. Okay, so this Becker's the question. Hold on, let me duplicate. I gotta go back. I just may have just created a ginormous error this whole dang time. Okay, I think oh god. I screwed this up the whole time. Wow. That's supposed to be 1 minus alpha over 3 pi, because I didn't use my brackets. What a noob. If this makes it work, I'm gonna laugh. Talking all about brackets and I don't even do it. Okay. So it appeared to... Oh, that still looks like it went... Okay. 1 minus alpha. Exponentiation of 5 over 3. Mass of the electron squared. Okay. So if we throw that whole jazz, this... Okay, so the claim is that's the Higgs mass. We've converted into charge. Squaring it. But should that be... It has negative charge squared, but once you square it, okay, it's going to go positive. So if we have that, okay, so we square it, goes positive. We're dividing the dimensions out. Oh, wait a second. I think I'm going to try to, first off, let's just get this ratio. Before we do anything else. I'm sorry, 2 coulombs. Sorry, this drives me crazy. Okay, there we go. Now we've got a actual charge. Okay. So now we can do this. Coulomb squared per electron mass squared. That's charge divided by mass squared. Okay. So, again, take the noob thing. It's going to come out to be an electrochemical equivalent, isn't it? I'm sorry. I'm just... Square root. Oh, hold on. Okay. Got a number. Actually, let me just see what the square root of this is, because I don't even know. Oh, come on. Let's try putting it this way. Sometimes Wolfram-Alpha doesn't like you to... Let me take the log of it? Okay, I'm just going to do this without the dimensions. I'm so bad. Let's go back to the calculation. All right. Boom. Okay. Those are our numbers. Those are our dimensions. Okay. Let's go back to our equation. Throw that in. Get our, oh God, big beautiful number here. Go. I feel like I need to have that negative thing be somewhere else because I think that's why they had it in there. So it would cancel out. There we go. Well, actually, no, that doesn't matter. That was... Oh, okay, yeah. Because it was, okay. So is that the same number? Yes, not negative. 653. 653, all right. I think that's why they did it. Okay. So now, this is the same dang number that we got before. It is, right? 1 over Let it get weaker. And then again, oh, hold on. No, let's add our dimensions back in. No. All right, so ampere squared. Square root. There, we'll get bigger now. It's going to get really big. Oh. I'm like, what am I doing here? I put it in there twice. I'm like, why is it returning the same dang thing? All right, so that is far larger. Oh, that's far too large. I'm just going to rip the dimensions out just because... Oh, actually, no. Let's not do that. Mass. Charge divided by mass. So, coulombs divided by kilograms. All right, so those are our effective reference ones. Oh, yeah, that's... Does this make sense, though? Because once you start getting up to, like, I think, like, the loop for the top quark, it actually gets towards the strong force, which is technically 1, so maybe this does make sense. That's also pretty close to Joe 1. It's like 11.7 or so. Yeah. I don't have an answer. I'm not going to waste your all's time here. We're just going through computations, so... That's all I really got, so hey, thank you all for joining me on my struggling through trying to explain something, getting to a point, and then getting a sidetrack, because that's never happened before. But thank you all for watching. Take care of yourselves, everyone. It's a wacky and wild world out there, but let's do it better tomorrow. Peace out, everybody.